This is another electromagnetism tutorial, and it's going to be the last one as well. And here I'll be starting off with just a few differences between AC and DC. You've done both of these now. You've done the AC generator and the DC motor. So based on that, we'll just sum up a few differences. Firstly, AC, we saw that when you have a, say, like a graph like this, you can see that it has varying EMF or varying current. Its magnitude is varying. It keeps changing with time. On the other hand, if you see a graph for DC, you'll actually see just one straight line which is just parallel to the x-axis. Say it represents time over here. So the magnitude remains constant with time. Remains constant. Now another difference would be that if you remember from AC generator, we said that the current first flows in the ABCD direction and then it switches over to TCBA. So you can see that it's not just one direction that it flows in, it flows in both directions and keeps reversing its direction of flow in the circuit. While you look at DC, it's just one direction, unidirectional flow. So it's not going to change, reverse, nothing, just one direction. And a third minor difference is the source that you get these two from. AC is, of course, what we just studied, that's a generator. That's how you get AC. For DC, you have your cells and batteries. I'll try and draw one here. Okay, so this is a cell. It doesn't look like one, but it is. And now I'm also going to just tell you a few differences, a few obvious differences between AC generator and DC motor. So let's say gen over here, motor here. So biggest difference is that in generator you provide mechanical energy and this gets converted to electrical energy, electricity that is. So you give it a certain rotation and it gives you back electricity in return. The motor, on the other hand, you give it electricity and in turn it'll rotate that axle over there. So it'll give you mechanical energy back. While in the generator you're giving it mechanical energy. That's a major difference. Another major difference is the principle that the two work on. Generator, AC generator works on the principle of electromagnetic induction. I think you all know this. And the motor works on the principle of the Lorentz force, Murray Lorentz force here. Actually, if this is asked, then you should write the whole thing about how a current carrying conductor, when placed in a magnetic field, experiences a force. That's a principle that the motor works on. So I'm citing Lorentz force here. I don't have so much space to write all that, but this is the main difference. And you could, I think, another difference. It's not exactly a difference, but I think it's something you should remember. Remember that when you're talking about generator, we take the right hand rule. Fleming's right hand rule comes into play. Over here, it's left hand rule. It's not a difference. If you're asked differences, please don't write this. I'm just telling you this because if you go wrong over here, then in all your numericals, you get everything in the opposite direction. So easy way to remember this: Lorentz force for motor, same L for left over here. That's also motor. So that's it in differences. And there is one major advantage of alternating current, and that is that its EMF can be changed. We saw that the graph for DC is just a straight line. You can't do anything with it. You can't change it around. You can't play around with the EMF. But in AC, you can step up, or you could step it down. Why is this useful? I'm going to tell you right now. For alternating current, you have these generators, these powerhouses set up all over the country, and I'm sure you've done this under the second chapter of electricity, that's household circuits. But these these generators, they generate a huge amount of current, and this is then in turn provided to some of them are made just for one city. So you could imagine that how many lines they'll have. Each one separates into certain areas, and then you have another substation over there which distributes to each house. So we're talking about huge distances here. We're talking in hundreds of kilometers. And if you remember from the second chapter, we had the formula P is equal to VI. Now, one thing is for sure, when we're transmitting from the generator sector to the houses, we have a constant power in watt. The unit is watt, so a certain watt amount of power. So we need to keep this constant. And with that, we can say that there's an inverse relation between V and I. If you increase V, I decreases. If you decrease V, I increases, because that product is a constant. Also, you would have studied the Joule's law of heating, where you would have, if you remember correctly, when you increase I, that is the current, the heating effect produced by the charge, the current, heating effect increases. And similarly, if you increase R as well, same thing happens. If you increase the time, same thing happens. R is cross resistance. So when you're transmitting, say I'm going to take a different color and do it. You're transmitting this over here. There is bound to be a certain loss in the energy in the form of heat energy. You can't have 100% efficient uh, transmission of the electricity, so some of it is going to be lost in the form of heat energy. So we can't minimize it completely, but we can definitely reduce this heat energy. And how do we reduce it? By reducing R of the wire. Now, I think that's dealt with in the first or second chapter, one of them. We're not looking at this right now. We're not looking at time right now. We're looking at I. So we need to reduce I. Now, just look at this relation that we derived here. If you want to reduce I, we need to increase V. Now, this is where your alternating current or alternating EMF comes into play. You can alter the EMF or the voltage of AC, and so we're going to use that to step up the voltage when we're transmitting over long distances. So as a result, I decreases, and so the heat that is given out in the process is decreased. So less heat, less energy is lost when you do this. So this is definitely more efficient, and to do that we need to increase V. Now I'm going to go over the transformer. The transformer is a device that actually helps us do this. So I'm not going over the whole construction of it right now. I'm going to do a rough drawing right now first. So it's like a cube. It has a core in the middle, and you have two coils on either side. Something like this. This is called, say you have your input over here. Input means that this coil here is connected to an alternating current source. So you're providing the transformer input in the form of current over here. Then this is called the primary coil, denoting it by P. Similarly, on the opposite side, you're going to have a few more coils. These will be called the secondary coils, and you can guess this will be output. Now, this uses the principle of electromagnetic induction. You have current flowing in this wire. I'll denote it by a different color. Current is flowing here, and remember that the magnitude is changing. Why is it changing? That's because we've taken AC over here. So this is varying EMF, so it's also varying current. I don't know how to denote it. Maybe just to make a sort of scribble over it. It's varying. And you know, because of electromagnetic induction, the reverse of electromagnetic induction will also be true. So instead of inducing EMF, Now this EMF over here, varying EMF, will produce a varying magnetic field as well. I'll make it in green and I'll scribble all over it just to show it's varying. Now this is the core over here. This is the core of the transformer. Now you apply the reverse of electromagnetic induction. You have a magnetic field, bearing magnetic field over here, and you have a conductor over here. So what it's going to do is induce an EMF in it, which will also be varied. So as a result, you have varying EMF. Right. So also note that the characteristics of this yellow part, the EMF in this yellow part and the EMF in the green part, that's primary and secondary, will be the same. You could also look at this in another way. I'm going to go back. Say you have a current over here. Now it's actually like a process of copy pasting. You select this part induces a certain it doesn't induce, sorry, it causes a certain magnetic field to come into existence in the core, and as a result this gets copied over here. Oops, I didn't copy. Yep, it becomes like this. It's like you have the green part here. It induces a magnetic field of the color yellow over here. Oops, that's not yellow. This is the magnetic field produced by it. So as a result, if you just apply the reverse, the same current is going to flow over here. The same characteristics. Now the EMF over here will be different from the EMF over here. It depends on two things. The first is the ratio of the number of turns of the coil in the secondary coil to the primary coil. We can denote it by NS by NP, and this ratio is called turns ratio. And NS by NP is equal to ES by EP, where E is the EMF. So you can see that if you increase the number of turns in S, your ES is also going to increase, so more EMF over there. If you increase NP, you're going to increase the EMF through P. So another rule now, you have, as I said at the beginning, step up and step down. Now if remember this is output here, input here. So if NS is more than NP, that also means we can say from this relation here that ES is more than EP, which means your output is more than your input. So that is a step up. And the inverse is also true. So you can just sum up this whole relation by saying NS by NP more than 1 for a step up, and it's lesser than 1 for a step down. If it's equal to 1, nothing's gonna happen because, well, you have the same turns over there. It's the same thing really. But also remember that none of this is ideal ever. It's a sort of machine, so it's not going to be ideal. There'll always be certain losses in the energy. It's not going to be exact. But for an ideal transformer, the power in the primary will be equal to the power in the secondary. So we can say VI over here is equal to VI in the secondary. And we can express V as EMF. So we can also say for an ideal transformer, EP into IS. Sorry, not IS, sorry, IP. I'm sorry, I'm just trying to fit it in at the bottom. Is equal to ES by IS. This is if your transformer is ideal. So that's all that is under transformer. The reason why you need a transformer is because while transmitting, you need to step up and step down to reduce the heat loss. Um, and also certain appliances in your house would need lesser voltage, and some would need a much higher voltage, so use it over there as well. And in your book, they've given certain energy losses in the transformer, which is what I was talking about right now. There, there's nothing to really understand there. You just need to learn that up. Um, and that's all there is in this chapter. I know it looks a bit tough when you first look at it, but if you just sit down and understand it, just understand it once, and you'll never go wrong over here. That's it for electromagnetism, and next time we'll be doing calorimetry.